Ryan and I are happy to be here. I just introduced myself a little bit. I've been with CFS for over 3 years now, but I met the company in 2019, as I mentioned, when they were looking at the site in Devens. For those of you who are Massachusetts residents, I think it was a pretty exciting thing to get this company to stay in Massachusetts and build all of those things I was talking about at our Devens campus. But I want Ryan to introduce himself, and then we'll jump into the presentation. I would say let's hold questions until we get through the presentation. Happy to take as many questions as you want to give us, but sometimes it's easier for us to get through the slides and then get to the Q&A, and we'll go from there. So with that, Ryan, why don't you tell folks who you are, what you do at CFS, and how long you've been there?
Yeah, totally. So I came in around the same time as Jess, either right before. I don't think we've ever come to a determination on who started first, but it's right around the same time.
I was May 2023. What about you?
I was June 2023. So I'm just a couple weeks after you.
Yep.
So I have a much different background to Fusion than Jessica. So Fusion has been kind of like the pie in the sky ideal that I've had in the back of my head for most of my life. I come from a really nuclear positive household. My dad's uncle is one of the premier nuclear engineers in the United States. And so I grew up with just like this healthy understanding of radiological sciences and fundamentally believe that fusion is the pathway. It's the holy grail of energy technology. So Jessica came into Fusion as a byproduct of being local to Devens and just being involved with, getting involved with the company. But for me, I was looking for this specifically. I graduated with my degree in nuclear engineering. And when I was in school, I graduated in 2016. All my professors were like, there's nothing worth pursuing in fusion in the world. Stay in fission. And I thought that, fusion is really exciting. I think that it was right around the corner. And so I actually had to learn fusion science in my garage with some friends while I was an undergraduate. So seeing it go from, garage science to a multi-billion-dollar international research venture has been one of the coolest things that I've ever gotten to be involved with. So, that's pretty much how I came to CFS. Is CFS, I think, has the best opportunity to break net positive energy with a fusion device. So what I do at CFS, I'm a senior systems engineer, and I work kind of jack of all trades, master of none. I work on a lot of things, but mostly systems that move heat around. So we have tokamak vessel conditioning, cryogenics, and then molten salts. All of those are in my engineering and research purview.
And we will talk more about all of those things as we go through the slides.
Definitely.
Oh, keep going, Ryan. I just wanted to make sure like you were listing off all these things. So.
Oh yeah, no, you hit the nail on the head. That's exactly where I wanted to transition to get started. I think.
All right.
Yeah, that's my background. Let's hop in.
Super. So folks can see the slides here. Okay, great. Thank you. So I think we all probably at this point, unless we're living under a rock, know where energy demand is going, and it is distinctly upward, and one might even say looking like a hockey stick. And as we think about how are we going to meet those energy demands, it's not just about building new plants. It's about innovation and about finding a new clean energy source. And while everyone agrees where energy demand is going, we feel strongly at Commonwealth Fusion Systems that fusion is a solution to this challenge. We're not necessarily here to displace any other energy sources, particularly at this time as we're getting started. It's really an all of the above type of need right now and a new source. But we're excited about the prospect of what fusion energy can bring to this landscape. But what is fusion energy? I have a feeling the folks on this call have some knowledge of fusion energy, but we're still going to get into the basics of it and maybe a little bit of the weeds, and then more about the company itself and why we're so confident that we're going to be the first to commercialize fusion energy. But let's get into what is fusion energy first, and I'm going to turn over to Ryan for that.
Sure, thanks, Jess. So fusion, nuclear energy nuclear energy production comes in two flavors: fission and fusion. Fission is what exists in all commercially viable nuclear energy production machines in the world. Fusion is what we are trying to do. Fusion is when you take two small atoms, in our case, deuterium and tritium, which are both isotopes of hydrogen, and you put them under immense pressures and temperatures, and you get them to fuse into a heavier element. In this case, helium. And so when you actually make this interaction happen, when you break the Coulombic barrier, you release a bunch of energy, 7 times the amount of energy per reaction than fission, and 200 million times the amount of energy per reaction than coal. So the energy density for fusion is significantly higher than any other fuel source in the world. So on top of the fact that it produces more power per interaction than any other known energy production method, fusion has a bunch of different facets that make it really interesting, a really exciting science and engineering venture to explore. First and foremost, it's really safe. So nuclear history and nuclear in general has a stigma against it because of the nuclear accidents that have happened in the past. With fusion interactions, we don't have to worry about that because it takes the amount of temperatures and pressures that you see in the center of stars, which is the only place in the universe that this interaction happens naturally. You need to have a ton of energy that goes into this reaction to make it happen. When that energy stops being dumped into the reaction just dies, and there's nothing else that can make it move forward. As opposed to fission, where once the reaction dies, let's say that you lose power, you still have to reject what's called decay heat from the reactor in order to make sure that you keep it from melting down. So fusion does not have that problem at all, because as soon as the energy stops being dumped into the reaction dies. Secondarily, it's very clean. So back to fission, uranium is a very dirty material. It's hard to get out. It's hard to get out of the ground, and then it's hard to produce in a way that makes it useful in reactors. And then after that, you're basically left with a bunch of materials that can be used to build nuclear weapons. And so there's a proliferation concern that's tied into this as well, that we can eliminate by moving towards a fusion future. One of the other comparisons that we get a lot is against other green technologies. And so the thing that fusion is able to provide is stability. We are able to provide firm baseload power as opposed to power that's provided by solar or wind, which is dependent on environmental conditions for energy production to happen. Like, you can't generate solar energy if it's the middle of the night or you're in a heavy rainstorm. And so we're not reliant on environmental conditions in order for us to be able to produce energy. And lastly, this ties back into the non-proliferation bit a little bit. It's scalable and secure. So we don't, by scaling up the science, we're not producing a bunch of materials that can be used to make nuclear weapons. And then on top of that, there is no real politics involved with securing the fuel sources that we need. So the two fuel species that we need are deuterium and tritium. Tritium is a byproduct of the fusion reaction, and so we make that in-house. And deuterium is readily extractable from seawater. Like 1 in every 6,000 hydrogen atoms in seawater is deuterium. So we can pull that out fairly readily. So on top of everything else, it allows us to kind of divorce ourselves from international geopolitics. So we are not the first company that's built a tokamak. In fact, there's about 150 of them around the world. And what makes our device so exciting is that we think, and we have some very good science to back this up, that our device is going to produce a net positive amount of energy. So you can see on this graph on the right, there's these little Q values. You can see a Q of 0.1, Q of 1, Q of 10, and Q of infinity. And all that Q value is the amount of output power divided by the amount of input power. So if you have a Q of 1, that means you're using up the exact amount of energy to produce the reaction as you're extracting from the reaction. Anything that's greater than that means you're getting more energy out of that reaction than it takes to make that reaction happen. So we can see that spark is sitting somewhere around a Q of 11. And what that means to us is that we can actually, with some fairly conservative physics, we have the understanding that when we turn this device on and we go and we perform a pulse operation, we are going to generate 11 times the amount of energy that it takes to actually make that reaction happen in the first place. So this is a concept that was originally proven to the world in 2022 with the National Ignition Facility, which, if you can see, it's this little blue dot on the graph. They were the ones that showed the world that fusion science can generate net positive energy. They had a Q of like 1.0001 or something like that. It required a laser array that takes more energy than the entire United States combined to output the energy of a toaster. And so that's not a very scalable science. And so what Spark aims to do is proof of concept that inside of a tokamak-based device, as opposed to the National Ignition Facility's device, which is a laser confinement device, our magnetic device, we're hoping to be the first team in the world to prove that we can make more energy out of this than it takes to make the reaction happen.
All right, I'm going to jump in with a little bit more about the company itself. But like what Ryan was getting at there is, and we probably could have explained a couple more things ahead of time. Spark is our prototype fusion machine. It is a magnetic confinement approach to fusion. There are other ways to get the fusion reaction to happen. Our approach is magnetic confinement using a machine called a tokamak. But you'll note, like, we're not called Commonwealth Tokamak Systems. We're called Commonwealth Fusion Systems. And our goal is commercializing fusion energy. If it proves that there's a better way to get there, we will pivot. But right now, we're confident that the tokamak is the most well, given how many have been built and the study and history behind them, we feel confident is the most likely to get us to commercializing fusion energy. And we have a team of people who've worked on tokamaks throughout the world, as well as a lot of other valuable experience. And we now have over 1,000 employees, despite the fact that we were founded only in 2018. I talked about meeting the company in 2019 when they first looked at the Devon site. And at that time, there were around 20 employees, just to give you an idea of how quickly we've grown. We are not your typical startup by any means. To Ryan's earlier point, like I started in May of 23, he started in June 23. Between that time, there were probably 100 more employees added to the company. Like that's how fast we've grown. We did spin out of the MIT and we continue to collaborate with MIT. That's a very important partnership to us. And we've got decades of research behind our team. I now have to update this slide. I'm a little bit embarrassed because not only do we have more than 1,000 employees, we've now raised $4 billion. So to that earlier point about, you know, where energy demand is going, it really gets at the, like, why is this company working so hard on this? And how are we raising this kind of capital? And it goes back to where that energy demand is seen as heading, and the reality of not knowing how we're going to meet it. So people are clearly excited and confident in our work, and that's how we've been able to raise $4 billion. And I will update this slide for my next presentation. We're also, before I get to this, you know, we believe very strongly in peer-reviewed publications, in being transparent about our work, and proving a validated approach. So we most recently released ARC physics papers, and Spark is our prototype that we're building in Devens, Massachusetts. There's only one Spark. We only need one prototype. After that, we'll be building ARC power plants. And again, we just released those ARC physics papers. We also have a demonstrated technology. So why are we so confident that we're going to be the company to do this? How have we been able to raise all this money? It's really a magnet technology, since we're doing a magnetic confinement approach to fusion in a tokamak. It's a magnet technology that we produce in collaboration with MIT, building the world's strongest magnets. And we demonstrated this back in 2021. So purchased the site in Devens in 2019. 2021. Met with Devens in 2019. Closed on the site in April of 2021. did the magnet test in September of 2021. And right after that was our Series B fundraising of $1.8 billion, which is still the largest clean tech raise and the largest Massachusetts raise. And now we're also in second place with our most recent raise of $1 billion more. So that technology showed that we could build the world's strongest magnet. Why does that matter to a tokamak to commercialize fusion energy? It allows us to build a smaller, more compact, more economical, efficient machine that we can then scale up to a power plant level. And again, the power plant is called ARC. The other thing I need to update on the slide is we're actually at over 80% complete of Spark now. So you're seeing an image here of what we call Tokamak Hall. At our Devens campus, we have a building called CFS1. That's like I said earlier, our offices, R&D, our manufacturing. We're manufacturing 3 types of magnets to go into this machine. And then in a separate building, that's the Spark building. And you're looking into Tokamak Hall, you're going to see some other pictures of that. And when we say that Spark is over 80% complete, for those of you who are familiar with tokamak, you may look and think, is that tokamak really 80% complete? The answer is no, but like all of the systems that are supporting it and the rest of the building, it's not just about building the tokamak itself. That is well under assembly now and moving very quickly, but it's the rest of that building and the support systems that Ryan's going to tell you a little bit more about that we're at that 80% mark now. Just to give you an idea of how fast we move, even in my experience of being in Devens and seeing a lot of companies come and grow there, I hadn't seen a company move this quickly. So purchased the site, again, closed on that in April of 2021. I know this says June 2021. I can tell you 2 weeks later, the site was cleared and getting ready for construction. And then you can see where we are now. 5 years later, you're looking at the Spark building. So that's that second building I was talking about. And the wings of this building are really important to understand the different systems that will make the tokamak work. And I'm going to have Ryan speak to that in just a moment. But on one side, we've got radio frequency. That's how we're heating the plasmas. That's what the wing that you're seeing on the right side coming into the tokamak hall. Towards the back is where we have battery technology that we will pull power from the grid, store it, and use it to get energy to the magnets. And then on the left side, you're seeing the cryogenics wing. That is Ryan's area of expertise. So he will explain more of that. And then the front of the building, you're seeing our diagnostics portion of the building. So it'll be office spaces. And you'll notice it's got a glass front. That was by design. And I think you'll also probably notice this doesn't look like a typical power plant. But even the thinking behind the designs of our buildings is meant to reflect like our transparency as a company and how we're approaching commercializing fusion energy and being open with our neighbors and our host community. And we do host community events on a quarterly basis. I'll talk a little bit more about that later, but I want to show you inside Tokamak Hall. And then I'm going to turn it over to Ryan to talk about the cryogenics portion of the building because it's in an exciting phase right now. So just to give you an idea of what we're looking at here in Tokamak Hall, all the kind of big orange pieces you're seeing on the bottom there are really stands to help us assemble the tokamak. Those will go away. The orange that you see at the top, the bridge cranes, those won't go away. Those will be staying in there. You'll also note that we've got, and I see we've got a question. Brendan, I was going to hold questions towards the end, but if you want to jump in with something relevant to this, you can.
Sorry, that was a stray keystroke, wrong window.
Oh, okay.
I didn't mean to raise my hand.
No worries. So again, Tokamak Hall, we've got 2 bridge cranes. Fun fact there. Ryan, tell me if I've got this wrong, but I think I don't. We didn't necessarily need 2 bridge cranes, but because of magnetic fields, we needed 2 bridge cranes. And like, this is the level of detail that we had to think about from day one in building this. You'll also notice even like the venting at the top and on the ceiling is not connected because we had to think about magnetic fields. But let me tell you about some of the big pieces you're seeing in the room. Towards the back is 2 halves of the vacuum vessel. Those are manufactured by a partner in Italy, Walter Tosto. The first half came in a very exciting way back in December via an Antonov plane. I think there's only 2 left in the world. It was a Ukrainian crew flying it from Italy, stopped in Ireland for fuel, landed in Portsmouth, and driven to Devons. So a real international affair there. And then the second half came via boat, much slower, much less glamorous, but nevertheless, we've got both halves now. It's very exciting. On the left, you're seeing a big D-shaped magnet, or it looks like a backwards D. So those are our toroidal field magnets. They're the kind of ones that steal the show. That was the one we tested back in 2021 with a strength of 20 Tesla. Actually, I think it got a little bit higher than that. I actually had the pleasure of attending that magnet test. I can tell you more about that later. But those are the magnets we have focused on first. And what you're seeing there is actually we've got, it looks like it's 2 on that stand. We've actually got, I think, 5 now in the stand, and there will be a total of 18. That's the symbol that you see for Commonwealth Fusion Systems. It represents those 18 toroidal field magnets. So it'll be 9 on one half of the room, that stand, 9 on the other. Then they will take the vacuum vessel and weave that inside. So precision measuring happening, or already happened, to make that work. At the bottom in the center of the room is the cryostat base. That was actually the first big piece to arrive in Tokamak Hall. And let me tell you, getting these pieces to Devons is a feat in and of itself. These are very large, heavy transports in some cases, awkward shapes. But we've managed to do that. And I often give tours in here to various groups. And I will just tell you, even if I go in that hall 2 times in 1 week, I will see new things. Like, that's how quickly we're moving. And this is also a good point to explain ways that we are continuing to innovate, iterate, get faster, get better. We're doing first of a kind stuff here. And so we have to create our own best management practices and improve upon those. So just to give you an idea, that TF case that you're seeing, that giant D shape again, and you're seeing it on the right too, kind of up closer. It used to take 50 days to weld one of those cases together. Inside there are layers we call pancakes that have high temperature superconducting tape. That's our secret sauce to our magnets. We'll talk a little bit more about that. But it used to take 50 days to put one of those cases together. Now we're down to 20. It used to take several days to put one of those upright in the stand, and now we do that in a matter of hours. So we're constantly improving upon ourselves and getting better. Ryan, can you jump in here and talk a little bit about the cryostat portion of the plant that they're seeing?
Yeah, totally. And before we get there, I just want to add on that the picture that's on the left was taken on June 1st of this year. And there's 2 magnets up there, and it's August 19th, and we have another 3 that have been installed. So just to Jessica's point about us being able to move through this very quickly, every iteration that we're going through this process, we're getting much faster. So a process that takes months now, we're expecting will take days by the time we get to arc level development. So I am the system responsible for the cryogenics plant. So these magnets that we have, they don't operate at ambient conditions. They utilize something called high temperature superconductivity, which is a little bit of a misnomer. Our magnets, they transition to basically an operational range where they can see resistance-less electrical transmission, but that only happens if they're below a threshold temperature. So for our magnets, that threshold temperature is at 80 Kelvin, 0 Kelvin being the coldest temperatures in the universe. So, us calling them at high temperature superconductivity is definitely a misnomer. We're still operating at close to the coldest temperatures that we can operate in the universe. But electrical resistance-less electrical transformation allows us to press on the plasma quite a bit harder, and it allows us to generate fusion in a much smaller operational envelope. So all in the top right picture, you're seeing a top-down view of our cryogenics plant. And so the cryogenics plant, it basically takes ambient temperature helium, drops it to the temperatures that we need for operation. So it brings everything down to for the toroidal field magnets down to 8 Kelvin to give us some thermal margin, because when we turn the machine on, there's a bunch of neutrons that go flying around and add kinetic energy to the magnets, but we want to make sure that that magnet's temperature stays below the critical threshold for the entire realm of operation. So basically this entire suite of equipment, we probably have a couple miles of piping, probably 1,000 miles worth of cabling, 1,000 valves, thousands of pieces of instrumentation. All of that is used specifically just to direct our volume of supercritical helium around the magnets to make sure that they stay below their operational temperatures. I like to say that we're following a very Tesla-type business model, in the sense that, like, if Tesla's ability to manufacture a car goes away, they still have value for their ability to produce magnets. And that's, I think, similar to how our business model is constructed, where, like, we are a fusion company, yes, and fusion is a way for us to capitalize on our fundamental technology, which is our magnets. And so at our site in Devens, we have 120,000 square feet.
Yeah, I think that's about right. Yeah.
We have 120,000 square foot factory floor where we are taking the base HTS material, so the superconducting material, integrating it into magnets, building the magnets, and integrating them into cases that can then be used to be put in our research device. And so real quickly, the mission, so all of the magnets that you see in this picture are being used or are going to go into Spark. And so I want to talk very briefly about the mission for Spark. So we were saying before, Spark is a research device, but what does that actually mean? The world has never seen a fusion grade plasma inside of a magnetically confined device. So there is a bunch of data that we need to see in order for us to make the next iterations of the design more cost effective, more tenable. And so Spark is our opportunity to do that. And so I'm glad that you brought this picture up. So this little orange building, Jessica called it the diagnostics building. We have what will very likely be the most sophisticated suite of diagnostics that will ever go into a fusion machine inside of that orange building. And the reason for that is we want to take all the data that we can now on this device, so that way by the time we get to the next iteration where we're going to need to make this cost effective, we have a background of information that we can use to make this design more cost effective and less risky. So that is the entire purpose for Spark. Spark is the way for us to research all the things that we need to research in order to make the ARC pilot plant more cost effective.
All right, I'll jump in here. To Ryan's point, again, only one Spark, and its product is really data as opposed to energy on the grid. It's not designed to put energy on the grid. It won't do that, but we will get a lot of learnings from it, and we will de-risk a lot of things. Spark will lead us to ARC, which is our power plant design. We've also selected the first location for that. I will get into that momentarily. But the things that will de-risk from Spark to ARC are economics, performance, technology. We've got all the receipts, and we'll be learning a lot. And we see Spark as a continuing probably research and knowledge gaining product, even once we move into the ARC era. In terms of where the first power plant is going, we announced that back in December of 2024, and it will be going to Chesterfield County, Virginia. And while this may seem like a disappointment for Massachusetts, Massachusetts is still our home and has a very large employment base, because that's where we're continuing to do the manufacturing as we even think about the power plant in Virginia. Growing manufacturing in Massachusetts, again, staying our headquarters and R&D, in addition to the home to Spark. But what we were hearing from potential customers, we did not have customers yet, but what we were hearing from potential customers is they wanted us in the PJM market. So PJM is like ISO New England, but in that part of the country, they're also the largest grid operator, I believe, in the world. And in addition to that, Virginia is also home to a lot of data centers. So the energy demand there has been growing faster than other parts of the country. And we knew we would get a talented work base. We've certainly found a talented work base here in Massachusetts. We feel confident the same will be true in Virginia. And we were able to find a site that was a greenfield site owned by the utility Dominion. And we will be leasing it from the utility and working with them as they want to think about diversifying their energy base. And we need to learn from them things like connecting to the grid. So it is an important partnership. We also have partnerships at like the state level, at the county level, in addition to having this utility partner. I want to share, because like this is part of my role. This site was going to be the site of a gas plant, and the local stakeholders and local community did not want to see that happen, and really were the reason why this site became available, because they said no to a gas plant. And so that was one of the first groups we met with in Virginia, in addition to, of course, state and local government. But we met with those stakeholders and said, look, here's what fusion energy is. Here's what it isn't. Here's who we are as a company. What do you think? Because it's important to us to go where we're wanted. That was true in Massachusetts, and we're following that model in Virginia as well. This site also has good access to highway and river infrastructure, and so far it's been a very welcoming community. We have not started construction there yet. I will talk a little bit about those timelines now. So again, we've kind of followed a path like, de-risking things, proving the technology, hiring the right team, raising the needed resources. To be clear, we're still pre-revenue type of company. However, to Ryan's earlier point, our magnet technology, we are starting to announce partnerships with other fusion companies who will buy our magnet technology. But we've proven the physics. That is an image of Alcator C-Mod, which was a small tokamak fusion machine at MIT that our founders worked on. We proved the magnet technology back in 2021 using that high temperature superconducting tape to make the world's strongest magnet. By the way, one of those D-shaped magnets can lift an aircraft carrier out of the water, just to give you an idea of the strength that we're talking about. Spark is under construction now, and we expect ARC, the power plant, to be online in the early 2030s. We will likely begin vertical construction at that site in 2028, but getting the site ready as early as later this year or early next year. We didn't have customers when we picked the site, but once we started making official plans, we did sign 2 power purchase agreements. The first was with Google. Every ARC power plant will produce 400 megawatts, and the power purchase agreement with Google for this particular power plant is for 200 megawatts to offset their carbon footprint. We'll still be putting energy on the grid, but they're early and confident investors in what we're trying to do, and we were able to make that agreement with them. Additionally, we signed a similar agreement with Eni, an oil company out of Italy, who has been an early and strong supporter of CFS, and that deal was valued at over $1 billion. This is very strong signals from the energy community and energy users that fusion power is truly right around the corner. This is also about creating an industry. So while certainly we want to succeed as a company, and I think Ryan alluded to this earlier, we are the largest and leading private fusion company in the world by both how many employees we have, as well as how much funding we have raised. And people ask, like, who's your competition? There's over 50 private fusion companies in the world. Some of them have different approaches to fusion, using machines called like a stellarator or a laser technology, zap pinch. I can't explain all of those, so please don't ask me to. Maybe Ryan can. But again, we're focused on the tokamak magnetic confinement. We are the largest and leading company by far. Really, our only competition is China. So just to give you an idea of like how do I know that? Why do we know that? There's 2 fusion companies, facilities you can see from space. The one we have in Devens and the ones they're building in China. So we know that they're working very hard on this as well, and we are conveying to our congressional delegation and really all of Congress, we have people working on this, that we need to be moving quickly in order to win that race. As a company, you know, we see this as a race against a lot of things, a race against energy demand, a race against climate change, and a race to be the first to commercialize it in this country. But it really is about building an industry, not just individual companies. We need vendors, we need suppliers who believe that this is going to scale up, that this is going to work. And we need them to invest in their own companies in order to meet our demands for all sorts of supplies. You know, I talked about one vendor who was the vacuum vessel. We have other vendors making those steel cases, the HTS pancakes go in. And so it really is about creating an industry, and that includes things like policy and regulations as well. As you might imagine, given my role, we also prioritize community engagement. We've brought over 1,000 community members in the Devens area, and we've invested in building long-term partnerships. We do anything from talks like this. We first met Jerry at the Doll Men's Club, but also school talks, career fairs. We actually just had an employee hiring fair at CFS last weekend. Ryan worked at. Ryan, were you at it? Is that what
I was not at it, actually.
Oh, actually, I was with somebody from our finance team who was at it today, and we had over 100 candidates show up, and I think we made 50 offers like on the spot. So like, again, continuing to grow. And I will just tell you from a community perspective, when this company first came to Devens, you know, part of my job was like, okay, how many jobs are we talking? What kind of jobs are these people? You know, is it just for people with PhDs in plasma physics? What are we talking? Because that's not the job market in the North Central Mass area necessarily. And I was assured there would be a range of jobs. That has certainly been true, and I would say exceeded expectations in terms of jobs. And I also just think it's really cool that we're the kind of employer where we've got over 100 people whose highest degree is high school working on our factory floor, working side by side with people with PhDs, collaborating, coming up with ways to make us better, faster. And I don't know a lot of companies that you can say that about. And I think it's something to brag about.
Yeah, Jessica, I'm glad that you said that. There was a slide earlier where you talked about like the ergonomics of Spark and like what it does to de-risk Arc. One of the biggest things that it does is it allows us to start developing the supply chain for, I guess supply chain and personnel chain to make fusion happen. So like there is no fusion industry that we have to pull people from right now. We have to pull from automotive, we have to pull from military, from semiconductor industries, from academia.
Yeah.
You name it. There is no industry that we have to pull from. So one of the things that Spark has allowed us to do is to start developing a pipeline of talent for people that can start taking over these machines as they come online down the road.
Yeah. Thank you for that, Ryan. So this is just an overall look at our campus, and we are continuing to grow in Massachusetts. At our site in Virginia, we expect that first power plant. And by the way, we did just submit our application to the PJM grid. That had to be in by April in order for us to meet the target of energy on the grid in the early 2030s. As part of that, we named the power plant. That was a requirement. So it is called the Fall Line Fusion Power Station. Don't try to make it into an acronym. It won't work. I've tried. And that's a really like telling moment for us because fusion was not a drop-down menu option in terms of grid applications until now. With our application to the PJM market. So we've done a pretty high level overview here of like who we are as a company, what we're building, what our timelines look like. We're excited to, as you can tell, Ryan and I are both passionate about this. We get excited talking about it. But we really, we're happy to answer your questions. I'll keep this screen up for now, but I'm happy to go back to some other images if you've got questions about that. So thank you for the invitation, and fire away if you've got questions for us. All right, Jerry.
Okay, just had to unmute. Traditional nuclear generates steam and then uses a turbine to generate electricity. And there are some other fusion startups that are generating electricity directly from their reactor. So how are you generating the heat?
So
Well,
I'm
You
gonna
generate,
I'm going to
you
jump in
gen-
at the high level and then turn to Ryan for
Yeah.
some more details. So Jerry, you are correct, or your assumptions are correct, that ultimately we are a fancy new way to create heat that'll make steam, that'll turn a turbine. That is how we will get energy to the grid. But how we create that heat is fundamentally different and really changes how you think about energy as more of a technology than a resource. So Ryan talked a little bit about our fuels earlier, deuterium and tritium. Deuterium is abundant. We will use our machine will have, I'm going to actually go back a couple images to show you what the inside of ARC looks like. Give me one moment. So between Spark and ARC, you'll notice a size difference, which is accurate. ARC is about 2 times bigger than Spark. Part of that is a molten salt blanket that will be part of the power plant that we will use. It has a few jobs, no pressure on the molten salt, but it has a few jobs. It will be the heat transfer. It's also a shielding mechanism for the neutrons, and we will use it to breed more tritium. So again, going back to that idea of energy as a technology versus a resource, we will have a closed loop system where we bring fuel in on day one on the back of a truck. We never bring fuel in again, and we don't need pipelines, for instance. But ultimately, yes, we're going to make steam and turn a turbine and put energy in the grid. Everybody knows how to do that. We don't need to invent new ways to do that. We just need to perfect using a tokamak to create the fusion reaction to make that heat source in a very new way. So Ryan, what would you add to that?
Yeah, totally. So the way that we actually produce energy with the ARC design is through neutron capture inside of the molten salt medium. So Jess hit the nail on the head. The salt is used as a neutron shield. But more succinctly, all of the energy that gets produced as part of the deuterium-tritium reaction is dumped into the neutron that comes out of that reaction. So you can think of them as like little relativistic bullets that come out of each reaction. They need to get stopped. And that stopping force, that kinetic energy transfer from those neutrons into the molten salt actually provides the heat that we need in order to turn a turbine. So once the neutrons interact with the molten salt will flow around a loop and will heat exchange down with water and then use that to actually turn a turbine. So Jerry, you asked a question about like direct electricity transformation from fusion devices. That is, I wouldn't go as far as to call it unproven. The science is fundamentally there. There's a big question on the scalability. And I don't think that the energetics, and we've done our own research on this to prove this out, but we don't think that the energetics make sense. We think that the tokamak that we're designing, it's going to have a much higher level of efficiency. We think that we're going to be able to use this device to show Q greater than 1. As opposed to the majority of the direct electricity transformation reactors in the world. They're just proof of concept devices. So they're just showing that you can actually produce energy using this particular method, and not necessarily that you can produce energy in a way, or not producing more energy than it actually takes to make that reaction happen in the first place. I think down the line, that's what they're looking at, but that technology is very, very, very nascent. And we think that there is a more direct line to commercialize fusion through the tokamak.
And I see we've got another question here.
Thank you, guys.
Thank you, Jerry.
Jessica, since you're partnering with MIT, is it fair to assume that the scientists at MIT and the scientists within your company have determined that of all the different approaches to fusion, that what you've selected has the most promise and you're running with it?
Yeah, so I won't speak for MIT. It is an ongoing collaboration. And we did spin out of MIT. I would note that we're also still, I think, the largest private funder of MIT research through DOE grants and other opportunities. So I will say that our founders and in the company itself, yes, we are most confident in the tokamak technology and approach to getting fusion energy on the grid on a commercial scale. But I don't want to speak for current MIT staff who I may not know.
Right. Okay. And you had mentioned that you were working with Dominion.
Yes.
To I don't remember the words that you used, but a layman's expression, to figure out how to bring the energy onto the grid in Virginia. So is that what I've just mentioned also something that needs to be learned how to do when you have such a large amount of energy that's being introduced to the grid?
Yeah, so again, each unit will be 400 megawatts, and that amount of energy was chosen on purpose because we knew it would work with the current grid system and the transmission system. And we have further confidence, and we'll have further reviews of that through the PJM application process. And obviously Dominion has a lot of experience in that region and with PJM. So we'll be leaning on them for some learnings, and they're learning fusion stuff from us. And then we're also leasing the property from Dominion. And I will just note, it's been an important and very good partnership. I have no doubt it will continue to be so. I don't know if folks heard about a potential merger between Dominion and NextEra. We don't expect that to impact our project or our agreements with Dominion. It's certainly something that we're keeping an eye on, but we don't expect any impact to our project as part of that.
And I just want to highlight too that adding 400 megawatts to the grid is not, that's actually not a terribly difficult thing. Like a commercial fission reactor is 1,000 megawatts. A coal plant in general is about 1,000 megawatts. So, it's just a different way to turn the turbine. But ultimately, adding the additional load onto the grid is that's one of probably the more well-known facets of this design.
Okay, Ryan, I appreciate that. Thank you.
Brendan, oh yeah, you're welcome. And if we're not answering your question, let us know, and we will do our best. And if we don't know an answer, we will be honest about that and be happy to get it from one of our other colleagues and get back to you. Brendan, what was your question? You are still on mute, Brendan, just in case you're trying to ask us something.
Sorry, I lowered my hand and forgot to unmute. So I've got a couple of questions, and just to say where I'm coming from first, I'm not a physicist, I'm not a chemist.
Me neither.
I'm just somebody who's watched too many YouTube videos. But my first question is, you mentioned that deuterium is relatively abundant in seawater, and I assume that extracting it from seawater or from another source is not that hard. But where does the tritium come from, and how does the tritium production factor into the energy equation that you talked about 10 or 11 times the output from the input?
Yeah, totally.
So I'll speak to supply first and then turn to Ryan for more of the science answer. So on the supply side, tritium is a byproduct of the fission process. Oh, I see a cat has joined our meeting. Excellent. tritium is a byproduct of the fission process. For us, it's fuel, so you can imagine we treat it differently. But a primary source right now would be Canada. And so we've secured the amount that we need at our Devon site already for the prototype. And just to share a little bit, I touched upon regulations and policy. This is a really good point to raise that. So, and then we'll get into the science part of the question as well. But our regulator for tritium, and that is really the only thing we need a license for, is the tritium. Our regulator is the Department of Health in Massachusetts. So the Nuclear Regulatory Commission made a decision, I think it was in 2023, to regulate fusion differently than fission based on the difference in risk profile. And this was a very important decision for the fusion industry. It impacts our costs, it impacts our timelines, but it really also should reflect the safety of fusion as a new clean energy source, because we were seen by the Nuclear Regulatory Commission as very different than the fission process in terms of our, what Ryan spoke to about no chain reaction, no opportunity for meltdown, but also no long-lived radioactive waste. We will have some activated material. I want to be straightforward about that. But our regulator is the Department of Health in Massachusetts, because Massachusetts is what they call an agreement state. So over 40 states are agreement states. And basically what that means is that the NRC delegates authority for licensing for fusion facilities to an agreement state. Therefore, the state is in charge of the licensing versus the NRC, the Nuclear Regulatory Commission. This is true in Massachusetts. It is also true in Virginia. They are also an agreement state, and we will be working with the Department of Environmental Quality and Department of Health there as well. And so beyond the supply of tritium, and then keep in mind, we will be breeding our own tritium as part of that molten salt blanket. So that's why we're confident in future supplies. But in terms of the science part of it, Ryan, are you able to answer that?
Yeah, totally.
Okay.
Yeah. So the molten salt blanket, like just saying, it's a multifaceted, a multifunctional design, and we basically need it to do a couple things. So the salt that we're using is something called FLIBE, F-L-I-B-E, for fluorine, lithium, beryllium. So when the deuterium-tritium interaction happens, it produces a neutron that's moving at a significant fraction of the speed of light. And it's actually moving so fast that it won't interact with the salt medium itself unless you have something to slow it down. So the beryllium, the beryllium component of the salt, it'll take a fusion neutron and slow it down into called the thermal range. But basically, it slows it down enough that it can interact with the lithium that's in the molten salts. And a thermal neutron plus lithium will produce tritium. And so this is actually our fuel cycle. So our fuel cycle lives inside of our molten salt blanket. So we produce the tritium inside of the molten salt blanket, and then we extract it using an extraction column that's in our plant as well. So the tritium that we need, aside from the initial onset that we need to produce our first reaction, basically what Jess said earlier, we need to bring in an initial source of fuel, and then we will never need to bring fuel on site again, because we have the ability to produce the constituent matter, the constituent components for the fuel in-house. Does that answer your question, Brendan, about tritium?
Yeah, it was basically like, where does the ongoing source of the tritium come from? And
Yep.
you just answered it, that it's within the cycle.
Yep,
So you're not paying extra energy somewhere else to make it. That Q factor of 10 you're talking about includes the production of the tritium.
That is correct.
And the second question, which we didn't get to yet, I didn't mention, is about what's your helium process look like? Because you mentioned that you need helium to cool the superconducting magnets.
Yep.
And so where does that helium come from? And does the helium for output of the fusion reaction, is that something you can use in the cooling cycle?
Sure, that's a great question. The interaction frequency, well, the number of interactions that we have inside of our fuel, like it's very, very minimal. There's so much energy that gets produced by each one of these reactions that we actually don't need that much fuel. So the amount of helium that we are generating is very, very insignificant in comparison to the amount of helium that we need to operate the magnets. So the helium that we do use, I don't remember where it's purchased from. I think local supplier. I think it's maybe Air Liquide. But the helium goes into a closed loop system. We use supercritical helium, and it just stays in gaseous form, and we keep it in a closed loop cycle. And so we don't actually need, barring the small little bit of leakage that we get over time, we actually don't need to have a consistent and replenished helium fuel source.
Okay, that answers my question. I was curious about how much it leaks, how hard is it to hold on to it, and
it's very
how does that compare to the world's stockpiles of what helium we have left?
Yeah, totally. It's a great question. We're leaking. We have a requirement for the design that says Spark needs to leak less than 800 meters cubed of helium per year. So it is a very, very insignificant amount of helium that we're losing over time. We probably have $2 or $3 million worth of helium in the system as it stands currently, and we should maybe have to replenish $1,000 or $2,000 of that per year just from nominal losses.
Yeah, and I had got this question from a very astute student once. So kind of two sides of it. Like one, we're producing helium, but like turns out it's not enough for not only a balloon factory, it's not even enough for a party. Right. So like we can't capture it. We're just releasing it into the air. At the same time, the student was like, wait a minute, you're using helium to cool the magnets. Like, isn't there a shortage? And Ryan's addressed this already, but like another answer I got from one of our colleagues is it is a closed loop system. So we're able to recycle some of it. We're also using liquid nitrogen, not just helium, to cool the magnets and other parts of the tokamak. So like,
yeah, it's a great
just wanted to kind of like share that as well. But it's something that we're mindful of, like with any materials or supplies that we need. If we know that there's like a shortage in the world, like we're keeping an eye on that and being mindful of it as we think about the future, because our goal is to build thousands of arcs, really all over the world. And yes, right now we're focused on finishing Spark and building the first arc. But I think we've demonstrated like we like to move fast at this company, and we like to only get faster at what we're doing. And the goal is ultimately thousands of arcs.
Yeah, it's a good point, Jess. The open loop portion of the design is through nitrogen. To your point, Brendan, helium is quite expensive, and there is definitely a shortage in the world. So we try and keep the helium within closed loop, but nitrogen is fairly inexpensive, and I think during normal operations, we need to have one tanker delivery every 4 hours of nitrogen in order for us to be able to operate. So that's really where the heat rejection and the materials that we need to reject the heat come into play.
Yes, Ron has a question.
And that's the end of my questions. I'm done. Thank you.
Thanks. Sorry, Brendan. I wasn't trying to shut you down.
No, I just wanted to be clear. I'm done. Next person.
Thank you.
Thanks.
Hi, I'm Ron. I'm a programmer, so I'm not an engineer. I'm not, but I'm very fascinated by this. It seems like this is great timing. Will this help alleviate some of the stress that AI is putting on the grid?
Yeah. So
I'll jump in there. So it's tricky, right? Like we could be a solution to the AI energy demand, but like also maybe seen as like allowing for more energy demand to happen. Nevertheless, we will be a new clean energy solution to the demand wherever it's coming from. Certainly AI is on all of our minds. But like, there's energy demands beyond that, that we want to be meeting as well. And we won't have like one customer or one user of our energy. It really is meant to be for everyone. But to your point on timing, right? Like that's a hot topic right now. Data centers are a hot topic right now. But I mean, none of us are blind to what we're paying at the pumps right now. And there's geopolitics, and there's the Strait of Hormuz, and thinking about energy as a technology versus as a resource, how that changes the political dynamics and energy security is really something I think that we're all mindful of as well. But we appreciate your interest, Ron. You don't have to be a plasma physicist or an engineer. I now tell fusion jokes and I nerd out about this stuff in ways I never ever thought would happen. I'm a political scientist at the end of the day, but this is exciting stuff. Like, and I'm, I'm from Massachusetts, so like I'm especially proud of like the fact that this innovation is happening in Massachusetts. I just think is super cool. Now, what's really depressing is when I go into schools and I talk about a Kitty Hawk moment and kids just give me blank stares. And that part makes me a little sad, but I'll come up with, other comparisons I'll give them.
Hey, Jess, can you go back to the electrical demand projections?
Yes.
I think it's the first graph.
Yes.
So to your point, Ron, we see a sharp departure in the middle of the 2020s in our energy consumption. Basically, year over year since the onset of computation, the world has used roughly 30% more energy in the next year, or 30% more energy for computation year over year, until 2023, where it jumped to 300%. What happened in 2023? OpenAI came online. So, we're seeing a sharp trajectory, a sharp departure from the existing energy demand trajectories, that seem to stem from this incipient point of AI. So, to your point, like this is the AI demand and the power that it's going to consume is really driving the need for there to be an alternative power source in the world.
But I will also argue that some of us are concerned about the climate. And I remember a time when I had 10 snow days in a school year. And when I go to schools now, or I have kids in school, and I ask them, how many snow days did you get? And they're like, 1, a half a day. Like, this is not normal Massachusetts. And I'm very upset about it. I know I'm the only one who still wants snow, but I'm upset about it. And so like, while the energy demand is like a big part of this, like there's a lot of us working at CFS who are just very much mission driven. And for instance, I think a really great example is one of our heads of production, Darby Dunn, came to us from SpaceX. And when she does a lot of talks, and when she talks to groups, she talks about the fact that she was known as the mother of dragons, as in the Dragon rocket, the one that just like brought the astronauts back, that one. Okay. So she's a big deal. And she talks about the fact that while she loved her work there and it was super exciting and challenging, she no longer wanted to focus on getting people off the planet. She wanted to focus on how do we keep them on the planet and like be happy and healthy and not sweating to death all year. So, a lot of us are at CFS for a lot of different reasons. Ryan was told you'll never work in fusion. It's not real. Look at him now. And I just want to go snowboarding for 4 months of the year.
And Massachusetts is going green a lot too. Like they're switching they're doing away with natural gas in a lot of areas and they're converting everything over to electricity as well.
Yeah. John, you had a question. Oh, John, you're still on mute. Oh, I can hear you. Sorry. No, sorry. I'm looking at your face, but go ahead.
I'm on the phone as well. I've been interested in like climate change since I was a kid. Like I think I first heard about it back in 1976. And just recently, I did a session with Gemini to just explore the ideas I've had over the years. And I heard that there's a company that does this. They built this molecule, sound like an early nanotech that supposed to be really good at pulling carbon dioxide out of the atmosphere. And apparently, the Gemini says they expect it to be on the market within 5 to 10 years. But, to use this on a really large scale, we need a lot of energy. So I'm wondering how quickly you're going to scale. You'll be able to scale yours up over the next 10 years or so.
Yeah, so like I said, our timeline is our first power plant energy output in the early 2030s, but you've heard a few examples already of how we've like ramped up our own knowledge, our own production, and capabilities. So right now, the focus continues to be finish the prototype, build the first power plant, early 2030s online. But we're also already thinking about the first block of power plants. So we work in parallel a lot of the time. And I'm going to give you a couple quick examples of that. So the company purchased the property April 2021. I mentioned that. We didn't approve the magnet technology until September of 2021. But we were that confident that it was going to work that we moved forward with buying the land, clearing the land, starting the construction project, right? Parallel paths. Similarly, people ask, why are you announcing where the first power plant's going? You haven't finished the prototype. Because one, we can't wait. We're in a race. But like, again, we're that confident that it's going to work that we will work on parallel paths so as to not waste time and lengthen out how much farther out it is before we get to the first block and then the nth power plant. So I can't give you exact timelines of like how quickly the scaling up happens, but I can assure you that Ryan and I and our colleagues work as hard and fast as possible. We're very tired, but we're going as fast as we can to get this on the grid because we know it's important.
We used to have plastered in our lobby our I guess not company motto, but it was like our own goal to have 10,000 ARCs online by 2050. That is no longer on the wall of our lobby anymore. We deem that that's quite a difficult problem to resolve. But that was the original scope that we were aiming for is on the order of thousands of machines within the next 30 years.
But it is going to take like other partners and other vendors as we continue to scale up. And we're working with them already, and we're working with suppliers and planning ahead for this. And again, thinking about expansion of our Massachusetts facility as we're growing and moving into the power plant phase of things. Yes, another question.
Yes, I was just thinking of the scenario of, let's just say for the sake of argument that we were looking at replacing, hydropower and, natural gas and other forms of power generation in just the Commonwealth of Massachusetts with fusion facilities like you're working on. Do we have a sense for how many it would take to fulfill Massachusetts power needs?
I don't.
And,
Yeah.
and I know that the power needs are changing, so that's kind of a moving target. But I'm just kind of thinking ahead at, is it 10? Is it 100? And then we get into the siting issues and what sites are appropriate, and just thinking of a future state, lowercase s, in Massachusetts. What would that look like to be fully built out?
Yeah,
and obviously it's a major public policy question, right?
Right. No, and I appreciate that. So I think if we do a calculation of like how many megawatts are used in Massachusetts on a daily basis, but I don't want to focus on that because right now we're not at a scale or a place to replace other sources in Massachusetts. What I will say is this: we don't need a lot of property to put these units. And while one unit produces 400 megawatts, there's no reason why we can't put more than one unit at one site, thereby doubling or tripling the megawatts produced. And I don't think we will need to have a doubling or tripling of the building size. Like the support systems can be shared, not for a 1-for-1 basis or 2-for-1 basis. I don't know what the ratio is, but some of those support systems wouldn't need to scale up on a 1-for-1 basis to support more than one unit. So that's one way to think about it, because it's a fair question about there's only so much land, and I get that. But also there's no reason why we can't consider utilizing brownfields where there have been other types of power plants or other types of industries and converting that to a fusion power plant site. Again, to give you an idea of like the size of the properties that we're talking about, the one where we're building in Chesterfield County, Virginia is 90 acres. It's not that big. And we think that could hold up to 2 ARC units.
And
Okay.
the opposite side of that, I did go through and just look at what the current energy demand for the state of Massachusetts was. It's like 10 gigawatts. So, you know, we're looking at about 20 machines for your hypothetical to cover all of the power demand for the state of Massachusetts.
Okay. I appreciate that.
Yep.
I'm just trying to think big picture, you know, the kinds of potential challenges and the roads ahead. And ultimately, part of that is certainly working with municipalities as well in terms of land use and helping them as various municipalities think about how they want to expand in a controlled way, being able to set aside certain parcels to at least be considered as potential future sites for something like this.
And I don't know your name because you're only coming up as A, but
Mike.
Mike, okay, not an A at all. So Mike, one thing I would point you to, so our website has a lot of amazing resources, and we recently released, like this past year, released a white paper on what do states need to do to attract fusion power plants, thinking about things like land use, like regulations, like policy.
Okay.
So yeah, we are definitely thinking on those terms. The team that I'm on is actually global affairs. So and it's kind of got 2 parts to it. It's people like myself doing community and local government affairs, but also on a state level. We have a federal person. We are talking to on an international level as well. In fact, before that NRC decision about regulating fusion differently than fission, we thought we were looking at other countries, including the UK, because they were kind of ahead of the game in terms of regulating fusion. Fortunately, the NRC made that decision. We were able to cite our first one in the US. But yeah, we issued a white paper on like what do states need to think about to attract fusion power plants, including Massachusetts. And Massachusetts, I would argue, is ahead of the game in a lot of ways. But also part of that that global affairs team, you know, we've got government affairs, we've got public affairs, but we also have an open innovation team, and they work with national labs and universities. They work on some of those DOE grants that we then funnel to universities and labs. So my point is, those 1,000+ employees we have are working on anything from techno-economics to, you know, our HR resources for Ryan and I as employees, to government affairs and regulations, to plasma-facing components and material scientists. We have such a broad array of knowledge and expertise that we've attracted to our facility. Most of those people work either full-time or hybrid in Devens, but we do have a workforce in other places as well. But we've really got an amazing team who are thinking about every level of detail and about, to your point, Mike, how do we do more? Like, you know, I can assure you our CEO, Bob Baumgard, is always thinking about the big picture and how we scale up. So I think we've got time for maybe 1 or 2 more questions if there are any. And I know Ryan shared our website. We do a lot of like amazing video content and updates. We'll do like a 6-month update that shows you inside the facility. I manage our community events. So if folks want to get notices about that, sometimes it's a talk, sometimes it's a tour. I do those on a quarterly basis. And Jerry can connect you with me.
I I'm gonna just piggyback off that too. So, on top of everything that Jess said, also on our website, we put every time we do a press release, we couple it with peer-reviewed science, and that's one of the things that drew me to CFS as opposed to any of the other fusion companies in the world, is that we are very transparent about what we're doing, and like we're developing good science that we're giving out to the world for free. And so, it's been fun to track the development of the science over time. And if you guys are interested in looking at this from a more technical lens, I highly encourage you to go and look at our list of publications that we've released over the last couple of years. I think we have 20 or 30 papers probably now that are all available for review. And all of them are through, like very premier journals, like Journal of Plasma Physics, Nature, Journal of Applied Physics, very high-end research journals. So if you guys are curious in the more technical aspects of it, you could follow that paper trail on our website as well.
Thank you for emphasizing that, Ryan. I'm now envisioning how I'm going to be spending some of my time in the days ahead.
It is a rabbit hole.
Just let some light summer reading, Mike. All right, any other questions? I want to thank you guys for inviting us. As you can see, we're always excited to talk about the future of fusion energy. So thank you, Jerry, for organizing this.
Thank you very much, Jessica.
All right, have a good night, guys.
Thank you.
Here's a quick question before you go.
Oh, John has one more question. Okay.
Thank you. Okay. Yeah, can you send us a copy of the slides so we can post on our website?
So typically I don't share the slides because, to the point I made myself tonight, it changes so often. And there's a lot of context that goes with it. So I know you have this recording, but like typically I don't share the slides because they're just updating so frequently that it would become stale very quickly. But I would encourage people to like go to our site, and there's a lot of resources on there. All right, thank you guys. Have a good night.
Okay, thank you very much, Ryan and Jessica.
Bye-bye.
Thank
Thank you guys.
Right.
Well, that was very interesting.
Yeah, again, I've heard it talk before, but the last time I heard it, I was sitting in the back room, and I didn't get a chance because we had about 35 people and couldn't get a chance to get up and talk to her. But the guy I sit next to at the Dull Men's Club every Friday is he actually built the first MRI in the world.
Really? Wow.
Yeah. And that's actually in Marlborough. His name is Moises, and he's from Brazil originally, but he used to work at Fermi Lab.
I live in Marlborough now.
Oh, you do? Have you heard of the Dull Men's Club?
I have not until tonight.
Okay. The Dull Men's Club meets every week. We have a 9 o'clock meeting called the Wizards, which usually gets about 10 people. And we talk mainly about science and technology. And the regular meeting gets different subjects every week, sometimes no subject. And we get about 35 people there. It's at the Southborough Senior Center.
Oh.
You can just show up if you want. The guy that runs the group, his name is Bill Harrington.
And what time of day is it again?
It's on Fridays. The Wizards meeting starts at 9 in the morning, and the regular full meeting starts at 10.
Okay.
And we're time crunched, so we
the Wizards meeting, which I run, ends at 9:45 because we have the women have to play cards. So they started complaining about us because we went over time a few times. But that's the first time I heard about Commonwealth Fusion, where I'm interested in Fusion. I had a video of Commonwealth. I had a video of a couple other Fusion startups. And I didn't realize at the time that Commonwealth was so far advanced. And since Jessica actually talked to us a few weeks ago, they got that extra $1 billion in the last couple of weeks, bringing them up to 4 billion.
That's incredible. I've seen at least one article about Fusion in MIT's Technology Review magazine, which is our alumni publication. But I haven't really studied it, and this was certainly exciting to listen to the state of the art from a key player in the industry and where they're at.
Yeah, well, the last time I was in Devens, the day I showed up, the day after I showed up, we had to go to the hospital to take a flight physical. And all the future flyers took off all of our clothes, put on a poncho, and we were naked all day in a poncho, staying around the hospital, mostly doing nothing.
Cameras were prohibited, right?
Yep. That was the summer of 1965.
Okay. Last night I read your